Good morning, chemists. I wanted to do two quick review problems from our lecture yesterday and then talk about section 10.5 of the book. First, I want you to calculate the change in enthalpy when 11.7 grams of propane, C3H8, fully combust. The delta H for that reaction is minus 2220 kilojoules. Then, hydrogen iodine can be created by combining diatomic hydrogen and iodine. Remember, those are both diatomic molecules. The delta H for the reaction is 53.0 kilojoules. How much energy is required to produce 7.45 grams of hydrogen iodide? Take a minute, work through those problems, see what you come up with. Pause the video while you're doing your work, and then unpause it to check your answers afterward. Is this what you came up with? Good. Now, moving on from the review from yesterday, I want to do a little bit on section 10.5. 10.5 is looking at states of matter, their properties, and some changes between them. Some of this is stuff you already know, so we'll move through it pretty quickly. Here we have the three phases of matter you're familiar with: gases, liquids, and solids, and some of the properties of them. What I want you to focus on here is that it takes some heat or some energy to move from a solid to a liquid, and some more heat or energy to move from a liquid to a gas. Likewise, if a gas releases some energy, if it cools, it turns into a liquid. And if a liquid releases some energy or cools even more, it'll turn into a solid. Interestingly, we don't think about this much, but all three could exist in the same place at the same time. Picture here we have some salt water, liquid water, icebergs with solid water, and then gaseous water vapor. Here's a nice diagram highlighting the energy changes between the three common states of matter and also through plasma, which you don't need to know about. Notice that enthalpy, or the energy of the system, is measured on the y-axis. And as you move from a solid to a liquid to a gas and then onto a plasma, it costs energy, or it requires energy. Those are higher energy states of matter. Likewise, moving from a gas to a liquid and then to a solid, you have lower energy states of matter. Evaporation is the first energy change I want to look at, moving from a gas to a liquid. Again, that costs some energy, that releases or increases the enthalpy of the reaction. We can define boiling point as the point at which evaporation takes place at 1 atmosphere of pressure. And that's just sea level, where we are right now. That's all I really need to know about evaporation for right now. Condensation, the reverse process, moving from a gas to a liquid, decreasing the energy in the system. That's the reverse of evaporation, so that also is going to take place at the boiling point. Melting is the process of a solid turning into a liquid. That's increasing the enthalpy of the system. Melting point, just like the boiling point, is the temperature at which melting occurs. It's a little bit less temperature dependent, so it's not so dependent, a little bit less pressure dependent, so not so dependent on the atmospheric pressure. Same idea, freezing, moving from a liquid to a solid, also happens at the melting point. Deposition is not a common change, moving from a gas to a solid. Large decrease in energy. Sometimes you see that happen on cold days when water vapor deposits into ice on your windshield. You have to scrape it off in the morning. And our final phase change is sublimation, moving from a solid to a gas, which is a large positive change in enthalpy. Again, not a terribly common phase change, but it does happen with dry ice or carbon dioxide, which goes directly from a solid to a gas. So the amount of energy involved in a phase change is a constant for each substance, and there's two terms I need you to know. I need you to know the enthalpy of vaporization, or delta H of Hvap, and that's the energy required to boil 1 mole of a substance, to go from a liquid to a gas. Enthalpy of fusion, delta H of fusion, is the energy required to melt 1 mole of a substance, and that's going from a solid to a liquid. Which one of those do you think would be greater? Think about it for a second. Pause the video and think about it for a second. If you said delta H of vaporization, you're right, because there we're breaking all of the intermolecular forces between a couple of molecules, rather than just melting, where we're only maybe breaking some of the intermolecular forces. And here's those values for water. And lo and behold, the delta H of vaporization is much, much greater than the delta H of fusion. Some good news, you don't need to memorize these. What I want to do next is apply these concepts of delta H of vaporization, delta H of fusion, see if we can do some calculations to predict energy changes during phase changes. First, a quick review. Remember that solids tend to have the highest IMFs. They're very close together, not moving very quickly, so lots of interactions between particles. Liquids tend to have some fewer IMFs, and for all intents and purposes, individual gas particles have no IMFs between them. So they're so far apart, moving so quickly, there's no time for interactions to take place. So as we move from one phase of matter to another, we're concerned about the energy it takes to break IMFs, or the energy released in forming IMFs. We can use what we call heating curves and some math to help us figure this out. Before looking at the energy involved in the changes, let's first look at just temperature changes across phases of matter and what we can learn there. As heat's added to a substance, the temperature of the substance may or may not change. And that's something that's maybe a little bit unfamiliar to us. Envision this beaker of ice water off to the side. During a phase change, that is to say, as that ice is melting, the temperature of the beaker won't actually change. You might notice that if you're drinking a glass of a cold drink on a hot day, that if you have ice in there, the drink stays cold even as that ice melts. However, between phase changes, the temperature does change. So this is to say, while the ice is melting during a phase change, the temperature remains constant. But once all the ice is melted and you're entirely in the liquid phase, temperature will begin to rise. The reason for that is that during phase changes, potential energy is changing, being added or removed. You can see a graph of that here, or a diagram of that here, where the potential energy or the orientation of the molecules is changing during a phase change. During sections where the temperature is changing, that is to say, temperature is going up or down, kinetic energy is changing. That is to say, the particles begin moving faster or moving more slowly. So again, during phase changes, potential energy changes. Within a phase, temperature or kinetic energy begins to change. So here's the general shape of a heating curve. We can envision that you start all as a solid, somewhere below the melting point of a substance. As you add heat to that system, the solid begins to warm up. Eventually, it reaches the melting point. For water, that would be 0 degrees Celsius. For other substances, different temperatures. At that point, the temperature change would stop while the substance undergoes a melting phase. During this melting, both solid and liquid are present. After all the solid has been melted and turned to liquid, the temperature would again begin to rise, and we'd again see some changes in kinetic energy as more heat is added. At this phase, just liquid is present. Once we reach the boiling point, that temperature change would stop again as the substance undergoes vaporization. Here, potential energy is changing rather than kinetic energy, and both liquid and gas is present. The last stage of the heating curve, after everything has been vaporized, you have no liquid left, you just have a gas. That gas can begin to heat up. And here, there's only a gas phase present, and again, it's a change in kinetic energy. Here's another general view of the heating curve. Take a second, look it over, and make sure you understand what's going on. It might be a good idea to turn the person sitting next to you, quiz them, and have them quiz you about what states of matter are present, and also whether kinetic or potential energy is changing during different sections of the graph. Take a second and do that right now. Do you agree? Let's look at adding a little bit of math to this. Recall the slides you saw a few moments ago, that the enthalpy of vaporization is the energy required to boil a mole of a substance, and the enthalpy of fusion is the energy required to melt a mole of a substance. Recall as well that you saw the values for water for these two phase changes. When we're within a phase, we can use this familiar equation of specific heat to calculate the energy change, Q equals mc delta T. You've seen this before, you've done some work with it before, I know it'll come right back to you. Remember that Q is energy, M is mass, C is the specific heat measured in joules per gram per degree Celsius, and T is a change in temperature. So we can use both those and the delta H, that equation, and the delta H of fusion and delta H of vaporization to calculate some of these values on our heating curves. Take a second and look this over. Notice that the different parts of the heating curve are solved using slightly different equations. When we're within a phase, here, here, and here, we're going to use that Q equals mc delta T equation. When we're in a phase change, we'll use some unit conversions, or factor label method, and delta H of fusion, or some unit conversions, or factor label method, and delta H of vaporization. Take a second and look this chart over. Make sure you appreciate the different steps that are involved. Being able to draw a heating curve or a diagram is going to be really useful in setting up these problems and helping to keep your work straight. So the first two example problems will involve drawing, we'll add in some math, and we'll have you do a few problems on your own. Example 1 says, draw the changes involved in taking ice at minus 4.5 degrees Celsius to liquid water at 38 degrees Celsius. Ice freezes at 0 Celsius. So I'd like you to draw a chart and label it with some temperatures, and then draw those changes involved. Take a second and do that right now. Pause the video. Did you come up with something like that? Remember as well, we're going to use Q equals mc delta T to calculate two of those changes. And we're going to use the delta H of fusion to calculate the phase change. For example 2, draw the changes involved in changing a liquid at 65 Celsius to a gas at 145 Celsius. This substance, which is not water, boils at 78 Celsius. Pause the video and try that right now. Is this what you came up with? Remember again, just like before, within a phase, we'll use Q equals mc delta T to solve for those temperature changes, the energy involved in those temperature changes. And here we'll use the delta H of vaporization for this substance to solve for the energy required during the phase change. All right, for example 3, draw all the changes possible when heating a solid below its melting point, eventually turning into a gas above its boiling point. Pause the video and try that right now. Did you come up with something like that? Nice. All right, now we're going to integrate some math. To do that, we need to remind ourselves of some of these constants. For water, we melt at 0, boil at 100. Not true of every substance. We have the three specific heats for water as a solid, a liquid, and a gas. Remember, this is talking about... All right, so I want you now to think about this. Calculate the energy in kilojoules required to change 7.5 grams of water from minus 11.5 degrees Celsius to 46.7 degrees Celsius. Remember again where H2O boils and melts. I'm going to set up the heating curve for you. We're starting off at minus 11.5 Celsius. Water is going to melt at 0 Celsius. And then eventually we're going to heat up to 46.7 Celsius. We're going to curve like that, like that, like that. So to solve this problem, you're going to need to solve Q equals mc delta T twice for two different phases of matter. And you're going to have to solve for the delta H of fusion as that sample of water melts. Take a minute and work those calculations now. You may need to refer back in the video to find the values for the specific heats and for the delta H of fusion of water. Pause the video while you work. Here's your three calculations. For that Q1, you're taking the mass of water, multiplying by the specific heat of ice, multiplying by the change in temperature. When water was in the liquid phase and was warming up, you could take that same mass of water, multiplied by the specific heat of liquid water, multiplied by the change in temperature of liquid water. These values are going to come out in joules. For the delta H of fusion, you can take the mass of water, use the molar mass to convert to moles, use the moles of water, and multiply by the delta H of fusion. That value is going to come out in kilojoules, So you got to remember to convert kilojoules to joules. Then just sum all three values, and you'll get the total energy needed for that process. Here's one more example problem. How much energy does it take to change 156 grams of water from 35 Celsius to 142 Celsius? I'll set up the heating curve for you. We're starting off at 35 degrees Celsius, warming up to 100, at which point water begins to boil, and then warming up to 142 degrees. So we're going to have some liquid water warming. We're going to go through boiling where the temperature plateaus and we change potential rather than kinetic energy. And then we're going to warm up our sample of gaseous water vapor. Just like before, we're going to use Q equals mc delta T twice. And here we're going to use the delta H of vaporization for water. Look back in the video, find the specific heats you need, find the delta H of vaporization, remember to check your units, and see if you can find the total amount of energy needed for this process to take place. Pause the video while you work. Hopefully you got something like this. Once you've converted your values from kilojoules to joules, sum all three, and you have the energy needed for this process. The final example problem doesn't deal with water, but deals with ethanol. So we're going to have different specific heats and different boiling points. The final question reads, how many kilojoules does it take to convert 125.5 grams of liquid ethanol at minus 80 Celsius to ethanol vapor at 80 Celsius? One last time, we'll set up the heating curve. Here we're starting at minus 80 degrees Celsius. We're going to warm that ethanol. And notice it's a liquid at minus 80, and it's going to stay a liquid until it reaches its boiling point at 78.4. 0 degrees Celsius is not an important number for ethanol. After 78.4, we're going to warm it a little bit further to 80 degrees Celsius. So in this change, we have liquid ethanol going from minus 80 to 78.4. We have a plateau as we go through the delta H of vaporization, and then we're going to warm it a little bit further to 80 degrees Celsius. Use the values are given here, and notice that delta H of vaporization is given in joules per gram, not joules per mole, and see if you can come up with the total energy change needed for this process. Pause the video while you work. Hopefully this is what you came up with. That's going to give you the energy change for all three parts of this warming equation, or this heating curve. Just like before, we'll sum all three, and I'll get you the total energy change for this process. Thanks for watching, guys. Check Veracross tonight for a little bit of homework to follow up on this.